The James Webb Space Telescope, JWST, which is the world's newest looking glass into the universe, can see light that has been traveling for over 13 billion years. But this light tells us more than just a story about time. It shows how our world has changed over time as it continues to grow. As we look back at the farthest galaxies, we're seeing what life was like a very long time ago. We're getting closer and closer to the Big Bang, the beginning of the universe. The Big Bang Theory, which is one of the main ideas in modern astronomy, boldly says that the universe has a clear beginning and a limited age. However, this idea of a single cosmic beginning has been met with doubt from the start, and problems with it are still present even in modern cosmology. It was thought to be true for many years, especially after the cosmic microwave background, CMB, was found in the 1960s. This background radiation, which is a soft, all-encompassing hum that can be felt all over the universe, fit perfectly with the idea that the early universe was hot and dense. But in the past few years, groundbreaking readings by the JWST have brought up old doubts and added to the list of questions about the Big Bang's validity. The JWST, NASA's cosmic time machine, has given us stunning views of groups of very old galaxies that are much bigger and more numerous than we thought possible. These discoveries have made us rethink what we thought we knew about the very beginning of the universe. The telescope looks back in time to when the first galaxies were being made, giving us a view that the Hubble telescope couldn't fully reach. Hubble was just not sensitive enough to pick up the very dim, redshifted light from these very early galaxies. But with the cutting-edge tools that JWST has, we can see back to the very beginning of time. As we go deeper into the dark, we come across an old mystery. How did the first galaxies really form? Does the universe as we know it really have a single beginning? In the beginning of time, the universe was hot, cloudy, and so dense that light itself couldn't move around easily. This means that we can't see any further back with light, no matter how strong our telescopes are. But we're not just limited to light. New developments in technology are making it possible to find gravitational waves from black holes meeting. This could give us a new way to look back into the early universe, maybe even into the event we call the Big Bang. Astronomers first noticed that galaxies far away looked like they were moving away from us in the 1920s and 1930s. This is where the Big Bang theory and its growing doubts got their start. This finding and Albert Einstein's theory of general relativity made it possible for the Big Bang model to grow. Einstein's equations said that a world that didn't change would be unstable and would need to either contract or expand. Seeing this growth made scientists think that galaxies must have been closer together in the past, which suggests that the universe began with a Big Bang. The expansion of the world has many important effects. As time goes on, things move farther apart, and the light they give off also changes, becoming longer in wavelength. It is known that shorter wavelengths are more powerful, so this redshifting shows that the universe has been cooling as it has aged. By going back in time during this expansion of the universe, we reach a point where everything would have been so hot and thick that neutral atoms would not have been able to exist. This would have caused a uniform, very hot glow. In 1964, astronomers Arno Penzias and Robert Wilson found the cosmic microwave background, a background radiation field that faintly echoes the universe's fiery beginning. This glow was proven. But as the JWST expands what we can see in space, scientists are finding things about the early universe that make the traditional Big Bang story less likely. We see huge, bright galaxies where there shouldn't be any, clumped together in ways that don't make sense. What else could explain these strange events if not the Big Bang theory? The Big Bang theory is based on the idea of a singularity, which is a point where the rules of physics don't apply because it is so dense and hot. It is said that this is where space and time begin. But this idea, while strong, has its limits. Imagine trying to describe how everything in the universe would fit into a single point that is infinitely dense. This is where we no longer understand. Observations and lab experiments have backed many parts of the Big Bang model. However, this initial singularity is still a mystery, which makes us wonder, could the universe have had a different kind of start? In its quest to learn more about the universe, science has found ways to make conditions that are like those in space. To match statements made about the early universe, scientists have made things like quark-gluon plasma and pairs of matter and antimatter. We have a good idea of how the universe has changed over time thanks to these tests and studies of the fluctuations in the cosmic microwave background. But there are still important secrets. For instance, if all of space used to be squished into a single point, then why is the temperature of the world so uniform? According to old ideas, different parts of space should have different temperatures because they wouldn't have had time to share energy or knowledge. Also, we might expect to see leftovers from the hottest times, like magnetic monopoles or changes in the shape of space, but none of these things are seen. This difference makes room for new options. Either these balanced qualities were built into the world from the start, or there was a mechanism that made them happen. Cosmological inflation, a fast expansion thought to have happened before the Big Bang, is one possible answer. Alan Guth, a scientist, came up with a revolutionary idea on December 7, 1979. He said that the universe grew exponentially before the hot Big Bang. It's possible that this inflationary phase is what makes the world look flat, uniform, and isotropic. The universe would change into the hot, dense state of the Big Bang after inflation. This would make it possible for galaxies, stars, and planets to form. Scientists now know, though, that even cosmic inflation can't explain all strange things. For example, the JWST's groundbreaking studies have found galaxies that were surprisingly big when the universe was young. This suggests that the rate of formation sped up, which inflation alone can't explain. The JWST's amazing features give us a view of the universe that has never been seen before. This infrared camera, which cost $10 billion, has taken stunning pictures of the early universe. These pictures show many massive, bright galaxies that existed when the universe was a very small part of its current age. Astronomers thought they had a good idea of how matter came together to make the first galaxies and stars, but the JWST results show that the process happened much faster than expected. Scientists are both excited and wary about these observations because they force some thinkers to rethink basic ideas about how galaxies form. Erica Nelson, an astrophysicist, says that massive galaxies seen in the first 500 million years of the universe's past don't fit with what we know about how the universe works. According to the JWST's early results, galaxies in this early period may have been much bigger and more common than was previously thought. They may have had masses similar to those found in large galaxies today, like the Milky Way. Cosmological models say that a galaxy this big wouldn't form until 1 to 2 billion years after the Big Bang. So this fast growth is a problem. According to Nelson's study, galaxies may be growing faster than thought. This could lead to the development of new theories about how galaxies evolve. Dark matter is a mysterious and invisible substance that is thought to make up about 85% of the mass of the universe and shape the structure of the cosmos on a big scale. According to standard cosmology, galaxies are thought to form inside large halos of dark matter. These halos attract normal matter with their gravity, which is how stars and galaxies come together. However, JWST observations put this idea to the test because galaxies are forming in ways that don't fit with what we know about how dark matter is distributed. Dark energy, a mysterious force that speeds up the growth of the universe, makes things even more difficult to understand. Some models say that early dark energy, a short-term rise in the quantity of dark energy, might have sped up the formation of galaxies, which might fit with what JWST found. But these changes have to fit into the bigger picture of the normal cosmological model, which has been able to explain how the universe has evolved on a large scale. The Big Bang theory is very interesting, but it's not the only way to explain how the world came to be. A number of different ideas have gotten a lot of attention, and each one offers a different point of view. In contrast to the Big Bang, the quasi-steady-state theory describes a world that has no beginning and where matter keeps appearing as it expands. According to this idea, new matter is made as galaxies move apart, which keeps the density the same. But it didn't take into account the CMB, which strongly supports the idea of a hot, dense early universe. More of a guess, the mirror universe theory says that there were two worlds at the start of the Big Bang, one moving forward in time and the other moving backward. This mirror world would change over time in the opposite direction of our own, showing how the history of the universe works. It's just a guess, but it makes me think that the world might be more complicated than we thought. The digital simulation theory adds to the idea that our universe might be a computer game made by a very advanced society. quantum entanglement and the strange way space-time works give the idea some philosophical weight. Even though it hasn't been proven yet, the simulation hypothesis raises questions about fate and reality that make us think about how we live. A popular alternative is the multiverse theory, which says there are an infinite number of universes, and each one has its own set of physical rules. This model says that changes in dark energy cause many events similar to the Big Bang, which creates a huge multiverse. At the same time, our universe grows, leaving no dark energy. This model suggests that there is a never-ending circle of birth, death, and rebirth. Each of these ideas gives us a different view of how the universe came to be and raises new questions about space-time and matter. Even though the Big Bang Theory is still the most popular explanation, new data and different points of view have challenged it and changed it. Because it is so sensitive, the JWST is about to reveal even more mysteries about the world. As the telescope continues its work, new spectroscopic data will make it possible for scientists can get more accurate readings of galaxies far away, which helps them learn more about how galaxies change over time. As the James Webb Space Telescope continues to look deeper into the universe, it will likely reveal new information that will change how we think about many basic cosmic processes. The formation and development of galaxies is an area that is likely to be changed a lot. Scientists used to think that galaxies were made up of small groups of matter that grew together over time due to gravity. But the JWST has found signs of galaxies that seem to have formed a lot earlier than was thought before. Not only are these early galaxies bigger and more common than scientists thought, but they also seem to have built complex structures in a lot less time than they thought was possible. This makes me wonder about the processes that cause galaxies to form. Even though gravity is very important, the fact that such huge galaxies were found in the early universe suggests that there may be other forces at play as well. One theory looks at the role of giant black holes, which might be one of the main ways galaxies grow. If these black holes formed early in the past of the universe, their strong gravitational pull could have sped up the process of matter gathering around them, which would have caused massive galaxies to form quickly. Also, the energy that these black holes gave off might have caused bursts of star formation, which would have sped up the growth of galaxies even more. The JWST's ability to find light from some of the universe's oldest galaxies also gives us new information about the universe's chemical makeup at different points in its history. Older telescopes, like Hubble, could see galaxies far away, but they weren't very good at picking up the weak light that very early galaxies gave off. JWST can see galaxies that were around in the first few 100 million years after the Big Bang because it has a bigger screen and can see infrared light. These findings show that the universe has a lot more types of chemicals than we thought. For example, the JWST has found galaxies that seem to contain metals, which are heavier than hydrogen and helium, a lot earlier than cosmologists thought they would. This makes me think that the process of stars forming in the early universe may have been more complicated. It's possible that the first stars added heavier elements to the gas around them much faster than we thought. In addition to new information about how galaxies form, the JWST's images give us new views on the structure of the universe as a whole. Cosmology has long been interested in how galaxies and galaxy groups are spread out in the universe. One of the main goals of the JWST is to look at how these systems changed over time in the universe. The telescope's ability to find trends in how galaxies clumped together in the early universe could tell us a lot about how dark matter and dark energy shaped the universe. Even though we can't directly see dark matter, we can get a sense of its influence by looking at how galaxies interact with each other through gravity. Dark matter, and how it affects the structure of the universe on a big scale, might be revealed by the way galaxies group together. The JWST will also make huge steps forward in the study of dark energy, the mysterious force that is speeding up the growth of the universe. Even though dark energy has been studied a lot over the last few decades, there are still many things we don't fully understand about it. Scientists can learn more about how dark energy has changed over time by measuring faraway galaxies and their redshift. Redshift is the way that light stretches as it moves through an expanding universe. Astronomers may learn more about how dark energy works and whether its effects have stayed the same or changed over time by comparing the rate at which the universe has expanded at different points in its past.